Hello, cosmic explorers, and welcome to the Cosmic Atlas, your gateway to understanding the magnificent universe that surrounds us. I'm so glad you've chosen to spend this time exploring the cosmos with me today. Right now, as you watch this, you're traveling through space at over 800,000 kilometers per hour. You're riding on a planet that spins while orbiting a star, which itself orbits the center of a galaxy that's hurtling through an expanding universe. And yet, you feel completely still. That's just the beginning of how extraordinary our cosmic reality truly is. Before we embark on this journey together, I want to ask you something. If you find value in what we explore today, if even one idea sparks wonder in your mind, please take a moment to hit that like button. It helps this content reach others who share your curiosity about the cosmos. And if you haven't already, subscribe to the Cosmic Atlas and ring that notification bell so you never miss our explorations into the unknown. Share this video with someone who looks up at the night sky and wonders about what lies beyond. Together, we can build a community of cosmic explorers. Today, we're going on an extraordinary journey. We'll venture to the edges of the observable universe and peer into the mysterious darkness that makes up most of cosmic reality. We'll witness the violent deaths of massive stars and the gentle births of new ones. We'll explore planets that rain diamonds, stars that spin 1,000 times per second, and regions of space where time itself behaves in ways that challenge everything we thought we knew. This isn't just a collection of interesting facts. This is the story of everything. It's the story of where we came from, what we're made of, and where the universe itself might be heading. It's a story written in light that has traveled for billions of years to reach our eyes, in gravitational waves that ripple through the fabric of space itself, and in the quiet mathematics that describe reality at its deepest levels. The universe is not only stranger than we imagine, it's stranger than we can imagine. But that's what makes it so compelling. Every answer we discover opens up new questions. Every mystery we solve reveals deeper mysteries waiting beneath. So settle in, relax, and prepare your mind for a journey across billions of light years and billions of years of time. Let's explore the cosmos together, the observable universe. When we talk about the universe, we often mean everything that exists. But there's an important distinction we need to understand: the difference between the entire universe and the observable universe. The observable universe is the portion of space from which light has had time to reach us. Since the Big Bang, approximately 13.8 billion years ago. You might think this means we can see objects up to 13.8 billion light years away. But the reality is more fascinating. Due to the expansion of space itself, the observable universe extends to approximately 46 billion light years in every direction from Earth. This creates a sphere around us, not because we're at the center of anything special, but simply because light has limits. Every observer in the universe has their own observable sphere, and many of those spheres don't overlap with ours. There are galaxies, stars, and potentially entire cosmic structures that we will never ever see, no matter how long we wait or how powerful our telescopes become. Why? Because space itself is expanding. This expansion, driven by the mysterious dark energy we'll discuss soon, means that distant regions are moving away from us, faster than light can travel through space to reach us. This doesn't violate Einstein's cosmic speed limit. Nothing is moving through space faster than light. Rather, space itself is stretching, carrying galaxies along with it. Think of it like dots on the surface of an inflating balloon. As the balloon expands, the dots move apart, but they're not actually moving across the balloon's surface. The surface itself is expanding. In the same way, distant galaxies aren't racing through space away from us. The space between us is growing. The most ancient light we can observe comes from the cosmic microwave background, the afterglow of the Big Bang itself. This light was released approximately 380,000 years after the universe's birth, at the moment when the cosmos cooled enough for atoms to form and light to travel freely. For the first time, before this moment, the universe was opaque, filled with a dense plasma of particles that constantly absorbed and re-emitted photons. This cosmic microwave background bathes the entire universe in a faint glow of microwave radiation. It's everywhere, in every direction at a temperature of about 2.7 degrees above absolute zero. This light has been traveling through space for over 13 billion years, stretched by cosmic expansion from visible and infrared wavelengths into microwaves. Remarkably, this ancient light is nearly perfectly uniform in all directions, varying by only about 1 part in 100,000. This extraordinary smoothness tells us that the early universe was remarkably homogeneous, but those tiny variations are crucially important. They represent quantum fluctuations from the universe's first moments, stretched to cosmic scales by inflation. These ripples in density would eventually grow through gravitational attraction into all the structure we see today: galaxies, galaxy clusters, and the vast cosmic web. When we observe distant galaxies, we're not seeing them as they exist now, but as they existed when their light began its journey toward us. The farther away an object is, the further back in time we're seeing. The most distant galaxies visible to the James Webb Space Telescope existed when the universe was only a few 100 million years old. We're seeing them in their cosmic infancy, when the first stars were just beginning to light up the darkness. This means that astronomy is uniquely a time machine. We can observe the past directly by looking at distant objects. The night sky is a living history book, with different chapters visible at different distances. But here's something that might keep you up at night: the truly vast universe, beyond our observable sphere. If the universe is infinite, as many cosmologists suspect, then the observable universe, vast as it is, represents an infinitesimally small fraction of all that exists. Beyond our cosmic horizon lie an infinite number of galaxies, stars, and worlds we will never observe, no matter how long we wait. Even more striking, due to the accelerating expansion of the universe, the observable universe is actually shrinking in terms of what we'll be able to see in the future. Galaxies that we can observe today will eventually recede beyond our cosmic horizon, their light unable to bridge the expanding space between us. In the far future, inhabitants of the Milky Way will see a much lonelier cosmos, with most other galaxies having disappeared beyond reach. Dark matter and dark energy. Here's one of the most humbling revelations in all of science. Everything we can see, all the stars, galaxies, nebulae, and gas clouds, makes up less than 5% of the universe. The other 95% is composed of substances we've never directly detected: dark matter and dark energy. Let's start with dark matter. In the 1930s, astronomer Fritz Zwicky noticed something peculiar about galaxy clusters. The galaxies within these clusters were moving much faster than they should, based on the visible matter alone. According to Newton's and Einstein's gravity laws, there wasn't enough visible mass to hold these clusters together. The galaxies should have flown apart long ago. Decades later, astronomer Vera Rubin made similar observations for individual galaxies. Stars in the outer regions of spiral galaxies were rotating just as fast as those near the center, which made no sense based on the visible matter distribution. It was as if the galaxies were embedded in massive halos of invisible matter. This mysterious substance, dark matter, doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all. We can only detect it through its gravitational effects. Yet it outweighs all the normal matter in the universe by a ratio of about 6:1. Dark matter forms a cosmic scaffolding, an invisible framework, upon which visible structures are built. It forms vast halos around galaxies and threads through space in enormous filaments, creating what astronomers call the cosmic web. This web is beautiful in its architecture. Long filaments of dark matter connect dense nodes, where galaxy clusters form, separated by vast cosmic voids containing very little matter of any kind. When we map the universe on the largest scales, we see this web clearly. Galaxies aren't randomly distributed. They follow the dark matter framework, gathering along filaments and at intersections. The structure resembles neural networks or the foam in a washing machine natural patterns that emerge from the mathematics of gravity and expansion. But what is dark matter? Despite decades of searching, we still don't know. Leading candidates include WIMPs, weakly interacting massive particles, axions, and even primordial black holes formed in the early universe. Experiments deep underground and in space continue searching for direct evidence of dark matter particles, but so far, it remains frustratingly elusive. Then there's dark energy, even more mysterious than dark matter. In the late 1990s, astronomers made a shocking discovery. By observing distant supernovae, they found that the universe's expansion isn't slowing down as expected from gravitational attraction. Instead, it's accelerating. Distant galaxies are receding from us faster and faster. This discovery earned the Nobel Prize in Physics and revolutionized cosmology. Something is pushing space apart, working against gravity's attractive pull. We call this mysterious something dark energy, though that's really just a label for our ignorance. Dark energy appears to be a property of space itself. The more space there is, the more dark energy there is. It doesn't dilute as the universe expands. This means that as the universe grows, dark energy's influence becomes increasingly dominant. In the early universe, matter dominated, slowing expansion through gravitational attraction. But as the universe expanded and matter spread out, dark energy took over, accelerating the expansion. Dark energy makes up about 68% of the universe's total energy content. Dark matter accounts for about 27%. The ordinary matter that makes up stars, planets, and us represents less than 5%. We are, quite literally, the minority constituency of the cosmos. The implications are profound. If dark energy continues to dominate, the universe will expand forever, growing colder and emptier over trillions of years. Distant galaxy clusters will recede beyond our view, then nearby clusters, then finally individual galaxies beyond our local group. The night sky will grow darker and lonelier as the universe ages. Some theories propose that dark energy might change over time, potentially growing stronger, leading to a big rip where even atoms are torn apart or weaker, allowing gravity to eventually halt expansion. We don't know which scenario is correct or whether entirely different physics might intervene. What we do know is that our understanding of the universe is fundamentally incomplete. The cosmos is dominated by substances we can't see, made of particles we haven't identified, following rules we don't fully comprehend. This isn't a failure of science, it's an invitation to discovery. A reminder that the universe still holds its deepest secrets close. Black holes, cosmic enigmas, few objects in the universe capture the imagination, quite like black holes, regions of space-time, where gravity is so intense that nothing, not even light itself, can escape. Black holes form when massive stars, those with at least 8 to 10 times the sun's mass, reach the end of their lives. After billions of years of burning hydrogen and helium, these stars exhaust their nuclear fuel. Without the outward pressure from fusion to balance gravity's inward pull, the star's core collapses catastrophically. This collapse is almost incomprehensibly violent. The core, containing about 1.5 times the sun's mass, collapses to a point just a few kilometers across in less than a second. The outer layers crash inward and then rebound in a supernova explosion, one of the most energetic events in the universe. But the core continues to collapse, crushing matter to infinite density at a point called a singularity. Around this singularity forms an event horizon, the point of no return. Within the event horizon, space itself is falling inward faster than the speed of light. Even a light beam aimed outward would be swept back toward the singularity. The event horizon isn't a physical surface you could pass through it without noticing anything unusual locally, but it represents a one-way boundary in space-time. This creates one of physics' greatest puzzles, the information paradox. According to quantum mechanics, information cannot be destroyed, but anything that falls into a black hole seems to disappear behind the event horizon forever, taking its information with it. Stephen Hawking and others have struggled with this paradox for decades, proposing solutions involving quantum effects at the horizon that might preserve information in subtle ways. Hawking's most famous contribution to black hole physics was the discovery that black holes aren't entirely black. Through a quantum process at the event horizon, black holes emit radiation now called Hawking radiation. This radiation is incredibly faint for stellar mass black holes, far too weak to detect with current technology. but it means that black holes very slowly evaporate over unimaginable stretches of time. For a solar mass black hole, the evaporation time is about Keir years, many times longer than the current age of the universe. But for tiny black holes, if they exist, evaporation could be much faster, potentially ending in a burst of energy as the black hole's final mass converts to radiation. Not all black holes form from dying stars. At the centers of most large galaxies, including our own Milky Way, lurk supermassive black holes, monsters containing millions or billions of solar masses. How these giants formed remains somewhat mysterious. They may have grown from stellar mass black holes through mergers and accretion, or they might have formed through direct collapse of massive gas clouds in the early universe. These galactic behemoths have profound effects on their surroundings. When matter falls toward them, it forms an accretion disk, a swirling vortex of gas heated to millions of degrees by friction and compression. These disks shine brilliantly across the electromagnetic spectrum, making supermassive black holes among the brightest objects in the universe despite their darkness. Some supermassive black holes launch enormous jets of matter and energy perpendicular to their accretion disks, extending for hundreds of thousands of light years. The mechanism involves powerful magnetic fields that channel infalling matter into narrow beams, moving at nearly the speed of light. These cosmic particle accelerators can outshine all the stars in their host galaxies. In 2015, humanity achieved a milestone, the first direct detection of gravitational waves from merging black holes. The LIGO detector sensed ripples in space-time caused by two black holes spiraling together and merging 1.3 billion light-years away. In the final fraction of a second, as the black holes coalesced, they converted three solar masses of matter into gravitational wave energy, briefly outshining all the stars in the observable universe. Since then, we've detected dozens more black hole mergers, as well as collisions between neutron stars. These observations have opened a new way of observing the universe, not through light, but through space-time vibrations. Gravitational wave astronomy lets us hear cosmic events that would otherwise remain hidden. In 2019, we achieved another first, an image of a black hole's silhouette. The Event Horizon Telescope, a planet-wide network of radio telescopes working in concert, captured the shadow of the supermassive black hole in the galaxy M87. The image shows a dark central region, the black hole, and its inner accretion disk surrounded by a bright ring of emission from the outer disk. This wasn't just a pretty picture, it was a confirmation of Einstein's predictions about how gravity warps space-time around compact objects. The size and shape of the shadow matched theoretical predictions with remarkable precision. A century after Einstein first proposed his theory of general relativity, black holes remain at the frontier of physics, where our best theories of quantum mechanics and gravity break down. At the singularity, densities and curvatures become infinite, signaling that we're missing something fundamental in our understanding. Reconciling quantum mechanics with general relativity, finding a theory of quantum gravity, remains one of physics' greatest challenges, and black holes are the testing ground where these theories must ultimately meet. The life cycle of stars are the engines of cosmic evolution, the forges, where the chemical elements are created. Understanding stellar evolution is understanding the universe's transformation from simple to complex, from a cosmos of hydrogen and helium to one rich with the diversity of matter. Stars are born in cold molecular clouds, vast regions of gas and dust scattered throughout galaxies. These clouds are typically quite stable, with internal pressure balancing gravitational collapse, but disturbances, shock waves from nearby supernovae, gravitational interactions, or collisions with other clouds can trigger collapse in dense regions. Once collapse begins, gravity takes over. A dense knot in the cloud contracts under its own weight, heating as gravitational potential energy converts to thermal energy. The collapsing region fragments into many clumps, which is why stars typically form in clusters rather than individually. Our own Sun likely formed in such a cluster about 4.6 billion years ago, though its sibling stars have long since drifted apart. As a protostar contracts, its core temperature climbs. When the core reaches about 10 million degrees Celsius, hydrogen fusion ignites, for hydrogen nuclei fuse to form helium, converting a small amount of mass to energy according to Einstein's famous equation, E equals mc. The energy released creates outward pressure that balances gravity's inward pull, and a stable star is born. This is the main sequence phase, during which stars spend most of their lives. Our Sun, a middle-aged main sequence star, will burn hydrogen steadily for about 10 billion years total, with about 5 billion years remaining. Smaller stars with less mass and lower temperatures burn more slowly and can last for trillions of years. Larger stars burn fiercely and die young. The most massive might last only a few million years. Eventually, all stars exhaust their core hydrogen. What happens next depends critically on mass for stars like the Sun. The inert helium core contracts and heats while a shell of hydrogen around it continues fusing. The star's outer layers expand dramatically, cooling as they spread out. The star becomes a red giant, enormous in size but cool in surface temperature. Our Sun will eventually expand beyond Earth's current orbit, though it will also lose significant mass, potentially sparing Earth from being engulfed. In the red giant's core, pressure and temperature continue rising. When the core reaches about 100 million degrees, helium fusion ignites, converting helium into carbon and oxygen. This phase is shorter than the main sequence, just a few hundred million years for a Sun-like star. Eventually, even helium runs out. For solar mass stars, that's the end of fusion. The core can't reach temperatures needed to fuse carbon. The star begins to pulsate and ejects its outer layers in a series of gentle puffs, creating a planetary nebula, beautiful shell of glowing gas surrounding the exposed core. What remains is a white dwarf, dense, hot ember about the size of Earth but containing about half the Sun's mass. A teaspoon of white dwarf matter would weigh several tons on Earth. The white dwarf doesn't fuse anything. It simply radiates stored heat, cooling gradually over billions of years. Eventually, it will become a black dwarf, a cold, dark cinder. However, no black dwarfs exist yet because the universe isn't old enough for any white dwarf to have cooled completely. Massive stars, those exceeding about 8 solar masses, have more dramatic fates. These stars can fuse progressively heavier elements in their cores: hydrogen to helium, helium to carbon and oxygen, carbon to neon, neon to oxygen and magnesium, oxygen to silicon and sulfur, and finally silicon to iron. But iron is the end of the line. Fusing iron doesn't release energy, it consumes it. When a massive star builds an iron core, it's living on borrowed time. The core grows until it reaches about 1 point for solar masses, the Chandrasekhar limit. At this point, nothing can support the core against gravity's crush. In less than a second, the core collapses from roughly Earth size to about 10 kilometers across. This releases an enormous gravitational energy, roughly 100 times what the star radiated. During its entire lifetime, a shock wave forms and blasts outward, tearing the star apart in a supernova explosion visible across millions of light years. Supernovae are crucial for cosmic evolution. They're the primary source of elements heavier than iron, gold, platinum, uranium, and all the metals that make up Earth's core. Every atom of iron in your blood, every atom of calcium in your bones, was forged in a star that died before our solar system existed. We are quite literally stardust, assembled from the remains of ancient stellar furnaces. The core left behind becomes a neutron star, a sphere of neutrons so dense that a teaspoon would weigh 1 billion tons. Some neutron stars are pulsars, spinning rapidly and beaming radiation like cosmic lighthouses. Others are magnetars with magnetic fields a quadrillion times stronger than Earth's. For the most massive stars, those exceeding about to 530 solar masses, even neutron degeneracy pressure can't stop the core collapse. The core continues collapsing to a black hole, and an event horizon forms, hiding the ultimate state of matter from our view. This cycle, birth, life, death, and recycling, has operated for over 13 billion years, gradually enriching the universe with heavy elements. The first stars contained essentially no elements beyond hydrogen and helium. They were population 3 stars, massive, luminous giants that lived fast and died young. Their supernovae seeded the universe with the first heavy elements. allowing the next generation of stars to form with more chemical complexity. Our Sun is a population-I star. Our ICH in metals, as astronomers call ore elements heavier than helium, formed from gas already enriched by billions of years of stellar evolution. The universe has matured from chemical simplicity to the rich complexity that allows rocky planets, liquid water, and ultimately life to exist. Galaxies and cosmic structure. Galaxies are the fundamental building blocks of large-scale cosmic structure, vast islands of stars, gas, and dark matter bound together by gravity. Our understanding of galaxies has grown from fuzzy spiral nebulae in early telescopes to detailed maps of their structure, formation, and evolution. Edwin Hubble's 1920s observations proved that many fuzzy patches in the sky were actually separate galaxies beyond our Milky Way, island universes in their own right. This discovery expanded our cosmic perspective enormously. The universe wasn't just the Milky Way. It contained billions of galaxies, each with billions of stars. Galaxies come in several main types. Spiral galaxies, like our Milky Way and Andromeda, have flat disks with curved arms spiraling outward from a central bulge. These arms are rich in gas, dust, and young stars, actively forming new stellar generations. The spiral pattern is maintained by density waves regions where gas is compressed, triggering star formation that lights up the arms. Elliptical galaxies range from nearly spherical to elongated footballs. They contain mostly older stars with little gas or dust, having converted most of their material into stars long ago. The largest galaxies in the universe are ellipticals, massive systems at galaxy cluster centers, containing trillions of solar masses. Irregular galaxies lack clear structure, lumpy collections of stars, gas, and dust without spiral arms or elliptical symmetry. Many irregulars are small, but some, like the Large Magellanic Cloud near the Milky Way, contain billions of stars. Our Milky Way is a barred spiral galaxy, meaning its central bulge has an elongated bar structure, rather than being spherical. The bar helps funnel gas toward the center, feeding star formation and the central black hole. Our solar system orbits in the Orion Arm, a minor spur between two major spiral arms, about 26,000 light-years from the galactic center. The Milky Way's disk is about 100,000 light-years across, but only about 1,000 light-years thick, relatively flat like a dinner plate. It contains 200 to 400 billion stars. Exact numbers are uncertain, along with vast quantities of gas, dust, and the mysterious dark matter that dominates its mass. We can't see the Milky Way's spiral structure directly because we're embedded within it. Viewing from inside, it's like trying to determine a forest's layout from ground level. But by mapping stars, gas clouds, and other structures, astronomers have pieced together our galaxy's shape, revealing a majestic spiral with several major arms wrapped around a bar-shaped core. At the Milky Way's center lurks Sagittarius **, a supermassive black hole containing about 4 million solar masses. It's currently quiet, accreting only small amounts of material, but evidence suggests it was more active in the past, perhaps when our galaxy collided with smaller companions. Galaxies don't exist in isolation. They're organized into groups and clusters, bound together by gravity. The Milky Way belongs to the local group, a collection of more than 50 galaxies, dominated by 3 large spirals, the Milky Way, Andromeda, and Triangulum. The rest are smaller dwarf galaxies, many orbiting the larger members like satellites. Andromeda, our nearest large galactic neighbor at about 2.5 million light-years away, is approaching us at roughly 110 kilometers per second. In about 4.5 billion years, Andromeda and the Milky Way will collide, though collision isn't quite accurate. The galaxies will pass through each other, their stars almost never actually colliding due to the vast spaces between them. But gravitational interactions will distort both galaxies dramatically, eventually merging them into a single large, elliptical galaxy, sometimes playfully called Milkomeda galaxy. Clusters are much larger than groups containing hundreds or thousands of galaxies bound by their collective gravity. The nearest large cluster, the Virgo cluster, lies about 65 million light-years away and contains more than 1,500 galaxies. Its gravity influences all nearby galaxies, including the local group, pulling us slowly toward its center. On even larger scales, clusters themselves organize into superclusters, vast filaments and sheets of galaxies, spanning hundreds of millions of light years. Between these filaments lie cosmic voids, enormous regions containing very few galaxies. When astronomers map the universe on the largest scales, this pattern emerges clearly, a cosmic web of matter arranged in interconnected filaments, surrounding vast empty voids. This structure developed from tiny quantum fluctuations in the early universe, stretched to cosmic scales by inflation. Regions slightly denser than average attracted more matter through gravity, growing denser still. Over billions of years, this led to a universe with pronounced structure, dense nodes where galaxy clusters formed, connected by filaments of galaxies surrounding empty voids. The largest known structure, the Hercules Corona Borealis Great Wall, spans roughly 10 billion light-years, so large that light takes 10 billion years to cross it. Structures this size challenge our understanding of cosmic evolution, as there may not have been enough time for gravity to organize matter on such scales. Galaxies evolve over cosmic time. Early galaxies, formed just a few 100 million years after the Big Bang, were smaller, less organized and more actively forming stars than today's galaxies. Many early galaxies were irregular, chaotic systems that would merge and settle into the spirals and ellipticals we see today. Major galaxy mergers are transformative events. When two spirals collide, gravitational interactions trigger intense star formation, starburst episodes, where new stars form at rates hundreds of times faster than normal. Gas clouds collide and compress, igniting waves of stellar birth. These starbursts are short-lived, cosmically speaking, exhausting available gas within a few 100 million years. The merger's aftermath often yields an elliptical galaxy, the product of two disks, thoroughly scrambled by gravitational chaos. The supermassive black holes from both original galaxies eventually merge, releasing gravitational waves and potentially triggering a quasar phase where the combined black hole shines brilliantly as it consumes surrounding gas. Our understanding of galaxies has evolved from simple classification to recognizing their complex life histories shaped by mergers, interactions, star formation, and feedback from supernovae and black holes. Every galaxy tells a story written over billions of years, encoding the history of cosmic structure formation, exoplanets and planetary systems. One of astronomy's most exciting revolutions has been the discovery of planets around other stars. For centuries, we could only speculate about whether planets existed beyond our solar system. Now we know they're abundant, perhaps numbering in the billions just in our galaxy alone. The first confirmed detection of an exoplanet around a sun-like star came in 1995, when Swiss astronomers Michel Mayer and Didier Queloz discovered a Jupiter-Mars planet orbiting the star 51 Pegasi. This discovery was revolutionary and puzzling. The planet, later called 51 Pegasi b, orbited extremely close to its star, completing an orbit in just 4 days. Nothing like this existed in our solar system. This was our first glimpse of the incredible diversity of planetary systems. We'd unconsciously assumed other systems would resemble our own, with small rocky planets near the star and gas giants farther out. 51 Pegasi b, a hot Jupiter, shattered that assumption. We quickly discovered that planetary systems come in bewildering variety. Several methods have revealed thousands of exoplanets. The radial velocity method detects the gravitational tug a planet exerts on its star, causing the star to wobble slightly. By measuring shifts in the star's spectral lines as it moves toward and away from us, we can infer the presence of orbiting planets, though this method works best for massive planets in close orbits. The transit method looks for tiny dips in a star's brightness as a planet crosses in front of it. From our perspective, NASA's Kepler Space Telescope used this method to discover thousands of planets, revolutionizing our understanding of planetary frequency and diversity. When a planet transits, we can measure not just its size, but also, if we observe the transit in multiple wavelengths, aspects of its atmosphere. Direct imaging, actually photographing planets, is extraordinarily challenging because Planets are millions of times fainter than their host stars and sit very close to them in the sky. But advanced techniques using coronagraphs and adaptive optics have succeeded in directly imaging several dozen planets, mostly young gas giants far from their stars. What have we learned? Planets are common. Most stars probably host planets. Our galaxy may contain hundreds of billions of planets, with tens of billions potentially Earth-sized and in their star's habitable zone, the region where temperatures permit liquid water on a planet's surface. But planetary systems show remarkable diversity. Hot Jupiters orbit very close to their stars, completing circuits in days. These gas giants likely formed farther out and migrated inward through interactions with the protoplanetary disk or with other planets. Super-Earths are planets larger than Earth but smaller than Neptune, a category missing from our solar system but apparently common elsewhere. We don't know if they're scaled-up rocky worlds or small versions of ice giants. Rogue planets drift through interstellar space without stars. These may have been ejected from their birth systems through gravitational interactions. Some estimates suggest rogue planets might outnumber stars. CIRCUMBINARY. Planets orbit both stars in binary systems, real-world Tatooine-like worlds with two suns in their skies. Planets around dead stars orbit white dwarfs or neutron stars, worlds that somehow survived their star's death or formed afterward from debris. The diversity extends to orbital architectures as well. Some systems have multiple planets in resonant orbits, where orbital periods maintain simple integer ratios. Others have highly elliptical orbits, unlike anything in our solar system. Some planetary systems are tightly packed with multiple planets orbiting closer than Mercury orbits our Sun. The search for potentially habitable worlds focuses on Earth-sized planets in the habitable zone of stable, long-lived stars. But habitable zone is a crude concept. Habitability depends on many factors beyond distance from the star: atmospheric composition, magnetic field strength, tidal locking, stellar activity, and more. Some planets might be habitable outside the traditional zone. Moons of gas giants could harbor life if tidal heating maintains subsurface oceans, as possibly occurs on Jupiter's moon Europa and Saturn's Enceladus. Planets with thick atmospheres might remain warm, enough for life well beyond the nominal habitable zone. The next frontier is characterizing exoplanet atmospheres, detecting biosignatures that might indicate life. When a planet transits, starlight filtering through its atmosphere carries chemical fingerprints. By analyzing this light spectroscopically, we can identify atmospheric gases. Future telescopes may detect combinations of gases like oxygen and methane together that strongly suggest biological activity. The James Webb Space Telescope and future missions like the planned Nancy Grace Roman Space Telescope will revolutionize exoplanet studies, potentially detecting biosignatures if they exist. We may be the generation that discovers whether life exists beyond Earth. The philosophical implications are profound. If we find life elsewhere, it suggests life is common, a natural outcome of chemistry and evolution under suitable conditions. If we search extensively and find nothing, it raises troubling questions about why we exist at all. The Fermi paradox in its starkest form. 8. The early universes. Universe's first moments remain physics' most extreme laboratory conditions that can never be recreated on Earth, where our best theories must meet and merge. Our cosmic story begins not with a bang in space, but with the beginning of space itself. About 13.8 billion years ago, all the matter and energy in the observable universe, everything we can see, was compressed into a volume smaller than an atom. Space, time, energy, and matter didn't exist separately. They were unified in ways we don't fully understand. We can't describe the first moment, the actual T equals 0, because our physics breaks down when densities and temperatures become infinite. General relativity predicts a singularity, but quantum effects surely dominated at these scales, and we lack a complete theory of quantum gravity. The Big Bang's initial singularity probably indicates our theoretical ignorance, rather than physical reality, but we can describe what happened moments later, in the first fractions of a second, with some confidence. As the universe expanded and cooled, it underwent a series of phase transitions fundamental changes in the nature of matter and forces. In the first tiny fraction of a second, perhaps around 1036 seconds, the universe underwent cosmic inflation. Space expanded exponentially, growing by a factor of at least 1026 in an incomprehensibly brief interval. This incredible growth solved several cosmological puzzles. Why the universe appears so uniform, why it's geometrically flat, and why we don't observe certain exotic particles predicted by particle physics. Inflation also explains the universe's structure. Quantum fluctuations during inflation were stretched to cosmic scales, creating tiny variations in density that would eventually grow into galaxies and galaxy clusters. In this sense, cosmic structure originated in quantum randomness, the universe's largest structures traceable to submicroscopic quantum jitters. After inflation ended, the universe was filled with a hot plasma of fundamental particles and energy. As it continued expanding and cooling, particles began to form. Quarks combined into protons and neutrons during the first microsecond. For the next few minutes, the universe was hot and dense enough for nuclear fusion, Big Bang nucleosynthesis, which forged the light elements deuterium, helium-3, helium-4, and lithium-7. Remarkably, calculations of Big Bang nucleosynthesis match observations of element abundances in ancient metal-poor stars and gas clouds. About 75% of ordinary matter is hydrogen, 25% helium, with traces of the other light elements precisely matching predictions. This agreement is one of the strongest pieces of evidence supporting the Big Bang model. For the next 380,000 years, the universe was opaque, dense, hot plasma where photons constantly scattered off free electrons. Light couldn't travel far without being absorbed and ray-emitted. But as the universe expanded and cooled, it eventually reached about 3000 Kelvin, cool enough for electrons to combine with protons, forming neutral hydrogen atoms. This recombination era made the universe transparent. Photons could suddenly travel freely through space. The cosmic microwave background radiation we observe today was released at this moment. Light that has been traveling through space for over 13 billion years, cooled by cosmic expansion from visible light to microwaves. After recombination came the cosmic Dark Ages, a period lasting perhaps a few 100 million years, when the universe contained only neutral hydrogen and helium. No stars existed yet to light the darkness. This was a blank canvas waiting for the first stars to emerge. Those first stars' population, 3 stars, formed from pristine primordial gas, containing no elements heavier than lithium. Without metals, as astronomers call heavier elements, the gas couldn't cool efficiently, meaning the first stars were probably very massive, perhaps dozens or even hundreds of solar masses. These giants burned brilliantly but briefly, ending their lives in supernova explosions that enriched the universe with the first heavy elements, seeding the next generation of star formation. Gradually, the first galaxies assembled from smaller structures, merging together, a bottom-up process, where small systems combined into larger ones. Early galaxies were smaller, more irregular, and more actively forming stars than typical galaxies today. One of the James Webb Space Telescope's primary missions is studying this era, observing the first galaxies and understanding how they evolved into the structures we see today. Already, JWST has revealed surprisingly mature galaxies existing earlier than expected, challenging our models of early galaxy formation. Throughout this early period, dark matter played a crucial invisible role. Its gravity helped gas collapse into the first structures, and its halos provided the gravitational wells where galaxies formed. Without dark matter, structure formation would have been much slower, perhaps too slow for galaxies to form within the universe's current age. The early universe's physics was simpler in some ways, fewer types of structures, more uniform conditions, but also more extreme. Understanding this era helps us grasp how the universe transformed from a nearly featureless plasma into the rich, structured cosmos we inhabit today. The universe isn't just vast and ancient, it's also home to some of the most violent, extreme, and mind-bending phenomena we can imagine. These cosmic extremes push the boundaries of physics to their absolute limits, creating conditions so intense they challenge our very understanding of reality. Gamma ray bursts, the universe's most powerful explosions, image an explosion so powerful that for a few seconds, it outshines the entire rest of the universe combined. That's a gamma ray burst, or GRB, the most energetic events we've ever detected in the cosmos. These catastrophic explosions release more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. When astronomers first detected them in the 1960s, they were completely baffled. Were they nearby, far away? Nuclear tests? Alien signals? It took decades to solve the mystery. We now know that gamma ray bursts come into varieties. Short GRBS, lasting less than 2 seconds, occur when two neutron stars collide in a cosmic demolition derby, merging into either a black hole or a supermassive neutron star. Long GRBS, lasting from seconds to minutes, mark the death throes of massive stars hypernovae that collapse directly into black holes, while spinning rapidly, creating jets of material that blast through space at 99.995% the speed of light. If a gamma ray burst occurred within a few thousand light years of Earth and pointed directly at us, the consequences would be apocalyptic. The intense radiation would strip away our ozone layer in seconds, exposing all life to lethal levels of ultraviolet radiation. Some scientists speculate that past mass extinctions may have been triggered by such events. Fortunately, the chances of this happening are extraordinarily small, but not zero. Magnetars, the universe's strongest magnets. Now let's talk about magnetars objects. So bizarre they sound like science fiction. These are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. To put that in perspective, a magnetar halfway to the moon would erase every credit card on Earth and fatally disrupt the electrical signals in your nervous system. Magnetars are born in the most violent supernova explosions, when a star's core collapses and begins spinning at incredible speeds, up to 70,000 revolutions per minute. This creates a dynamo effect that amplifies the magnetic field to incomprehensible strengths. The surface of a magnetar is a hellscape beyond imagination. The magnetic field is so strong it warps the very shape of atoms, turning them into elongated needles. Matter itself behaves differently under such extreme conditions. The crust, made of crystallized iron, is 10 billion times stronger than steel. Yet the intense magnetic stresses cause it to crack and shift in what we call starquakes. When a starquake occurs, the results are spectacular. The shifting crust releases vast amounts of magnetic energy, creating a magnetar flare, a burst of X-rays and gamma rays that can be detected across the galaxy. In 2004, a magnetar flare from SGR 1806-20, located 50,000 light-years away, was so intense it measurably affected Earth's ionosphere. If it had been just 10 light-years away, it would have caused a mass extinction. Pulsars, cosmic lighthouse. While magnetars are rare and violent, their cousins pulsars are more common and equally fascinating. Pulsars are rapidly spinning neutron stars that emit beams of radiation from their magnetic poles, like cosmic lighthouses sweeping across the universe. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student. The signal was so regular, pulsing every 1.3 seconds with incredible precision, that the team briefly wondered if they'd detected an alien civilization. They even nicknamed it LGM1 for Little Green Men. We now know thousands of pulsars, some spinning hundreds of times per second. The fastest known pulsar, PSRJ-1748-246 AD, rotates 716 times per second, so fast that its surface is moving at about 24% the speed of light. How does it not fly apart? The answer lies in the incredible gravitational force of the neutron star itself, holding together matter under conditions that would instantly vaporize any normal material. Pulsars are among the most precise clocks in the universe. Some are more accurate than atomic clocks, maintaining their rhythm to within millionths of a second over decades. This remarkable precision makes them useful as cosmic timekeepers. Scientists are using arrays of millisecond pulsars scattered across the galaxy as a kind of galactic GPS attempting to detect gravitational waves from supermassive black hole mergers by measuring tiny disruptions in the pulsar signals, quasars, and active galactic nuclei. Pulsars are cosmic lighthouses. Quasars are cosmic searchlights, the brightest sustained objects in the universe. The most luminous quasars shine with the power of 1 trillion suns, making them visible across billions of light-years of space. Quasars are powered by supermassive black holes, actively devouring matter in the centers of distant galaxies. As material spirals inward, it forms an accretion disk heated to millions of degrees, glowing intensely across the electromagnetic spectrum. Some of this matter doesn't fall into the black hole, but is instead blasted outward, in jets moving at near light speed, extending for hundreds of thousands of light years. When we look at quasars, we're looking back in time. The nearest quasars are billions of light years away, meaning we see them as they were in the early universe. Quasars were far more common in the cosmic past than they are today, suggesting that galaxies were more violent and turbulent in their youth. The supermassive black holes at their centers have largely consumed their available fuel and now sit relatively dormant, including the one at the heart of our own Milky Way. Active galactic nuclei, AGN for short, are the broader category that includes quasars. They represent galaxies with actively feeding central black holes, though not necessarily as extreme as the brightest quasars. The energy output from AGN can have profound effects on their host galaxies, driving away gas and effectively shutting down star formation, a process called AGN feedback. This cosmic thermostat may help explain why the most massive galaxies stopped forming stars and became the red and dead elliptical galaxies we see today. Fast radio bursts. The universe's latest mystery. Just when we thought we'd seen everything, the universe delivered a new mystery: fast radio bursts, or FRBS. These are millisecond-long pulses of radio waves from distant galaxies, carrying as much energy as the sun produces in a day, compressed into a time span shorter than a blink. The first FRB was discovered in 2007, hidden in archival data from 2001. For years, we detected only a handful, and they seemed completely random one-time events from different parts of the sky. This made them incredibly difficult to study. Without repeating signals, we couldn't point our best telescopes at the source to learn more. Then in 2016, everything changed. Astronomers discovered FRB 121102, the first repeating fast radio burst. This cosmic beacon kept sending signals, allowing scientists to pinpoint its location, a small dwarf galaxy 3 billion light-years away. The discoveries accelerated. We've now detected hundreds of FRBS and several repeat. In 2020, astronomers detected an FRB from within our own galaxy, originating from a magnetar. This was the breakthrough we needed, confirming that at least some FRBS come from magnetars. But here's where it gets interesting. Not all FRBS seem to fit the magnetar model. Some show patterns and characteristics that suggest different origins. Could multiple mechanisms create FRBS? Are some caused by colliding neutron stars? Black hole interactions? Something we haven't even imagined yet? The repeating FRBS are particularly puzzling. Some repeat seemingly at random, while others show periodic patterns, suggesting orbital dynamics, perhaps a neutron star orbiting another object. What makes FRBS particularly exciting is that they're tools for probing the universe itself. As these radio waves travel across cosmic distances, they interact with all the intervening matter, providing information about the distribution of gas between galaxies, the cosmic web itself. In this way, FRBS aren't just a mystery to solve. They're a new tool for understanding the universe. The study of extreme cosmic phenomena reminds us that the universe is far stranger and more violent than our everyday experience suggests. These objects exist at the absolute edge of what physics allows, in regimes where matter and energy behave in ways we're still working to understand. Each discovery raises new questions, pushing us to expand our theories and imagine new possibilities. Nothing in science has more radically transformed our understanding of reality than Einstein's theory of relativity. Before Einstein, space was simply the stage on which events unfolded, and time was the universal clock ticking at the same rate everywhere. Relativity shattered these intuitions, revealing that space and time are flexible, dynamic, and intimately connected. Einstein's revolution, the fabric of space-time in 1905. Einstein's special theory of relativity established that space and time aren't separate entities, but form a unified four-dimensional fabric called spacetime. The key insight? The speed of light is constant for all observers, regardless of their motion. This simple fact has profound consequences. If you're moving close to the speed of light, time slows down for you relative to a stationary observer, a phenomenon called time dilation. Your ruler shrinks in the direction of motion length contraction. These aren't optical illusions. They're real physical effects confirmed by countless experiments. 10 years later, Einstein completed his general theory of relativity, which extended these ideas to include gravity. The breakthrough insight was revolutionary. Gravity isn't a force pulling objects together, as Newton had thought. Instead, mass and energy curve space-time itself, and objects follow the straightest possible paths through this curved geometry. As physicist John Wheeler elegantly summarized, matter tells space-time how to curve, and space-time tells matter how to move. Think of space-time as a stretched rubber sheet. Place a bowling ball representing a massive object like a star on the sheet, and it creates a depression. Roll a marble nearby, and it will curve around the depression, not because the bowling ball is pulling it, but because it's following the curved surface. This is gravity according to Einstein. Time dilation. When clocks disagree, time dilation is one of relativity's most startling predictions, and it's been verified with extraordinary precision. The faster you move, or the closer you are to a massive object, the slower time passes for you relative to someone moving slower or farther from the mass. The classic example is the twin paradox. Imagine one twin stays on Earth while the other travels to a nearby star at near light speed. When the traveling twin returns, they'll have aged less than their sibling who stayed home. This isn't science fiction, it's established physics. Time has literally passed more slowly for the traveler dot. We see this effect with GPS satellites. They orbit at about 20,000 kilometers altitude, where Earth's gravity is weaker and they move at high speeds. Both factors affect time. The weaker gravity makes their clocks tick faster, by about 45 microseconds per day, while their velocity makes them tick slower by about 7 microseconds per day. The net effect is that their clocks gain about 38 microseconds per day, compared to clocks on Earth's surface that might seem trivial. But GPS relies on nanosecond precision to calculate positions accurately, without correcting for relativistic effects. GPS would accumulate errors of about 10 kilometers per day. Every time your phone shows your location accurately, it's confirming Einstein was right. Near black holes, time dilation becomes extreme. Close to the event horizon, time slows to a crawl from the perspective of a distant observer. If you could somehow survive falling toward a black hole, while your friend watched from a safe distance, they would see you moving slower and slower, appearing to freeze just as you cross the event horizon. Meanwhile, from your perspective, you cross the horizon in finite time, but you'd see the outside universe speed up dramatically, watching eons pass in moments. Gravitational lensing. When light, Benson of general relativity's most beautiful predictions, is gravitational lensing. Since massive objects curve spacetime and light follows paths through spacetime, light must bend around massive objects. Einstein himself was skeptical this could be observed, but in 1919, British astronomer Arthur Eddington tested the prediction during a solar eclipse. He measured the apparent positions of stars whose light passed close to the sun, finding they shifted by exactly the amount Einstein predicted. The news made Einstein an international celebrity overnight. Today, gravitational lensing is a powerful astronomical tool. When light from a distant galaxy passes near a massive foreground object like a galaxy cluster, the light bends and often splits into multiple images, creating Einstein rings and crosses stunning cosmic mirages. Strong gravitational lensing can magnify distant objects, acting as natural telescopes that let us see galaxies we couldn't otherwise detect. Weak gravitational lensing, where the distortion is subtle, allows astronomers to map the distribution of dark matter throughout the universe. By analyzing how background galaxies are slightly warped, we can trace the invisible dark matter that dominates cosmic structure. This has become one of our most important tools for understanding the universe's composition. The cosmic speed limit, speed of light to 199,792,458 meters per second, isn't just how fast light travels. It's the maximum speed at which any information or influence can propagate through the universe. This cosmic speed limit is built into the fundamental structure of space-time itself. Why can't anything move faster than light? As objects with mass accelerate, they gain relativistic mass, they effectively become heavier. The closer you get to light speed, the more energy is required for further acceleration. To actually reach light speed would require infinite energy, which is physically impossible. Only massless particles like photons can travel at light speed. And they always do, they can never move slower. This speed limit has profound implications. It means the universe has a causal structure, a cosmic hierarchy of what can influence what. Events too far apart in space and too close together in time simply cannot affect each other. This isn't a technological limitation. It's a fundamental feature of reality. Implications for space travel. The cosmic speed limit presents both challenges and opportunities for space travel. The challenge is obvious. Even at light speed, reaching nearby stars would take years, and crossing the galaxy would take tens of thousands of years. But time dilation offers a curious possibility. If a spacecraft could accelerate to near light speed, time would slow dramatically for the travelers. At 99.999% light speed, time dilation is so extreme that the crew might experience just a few years while decades or centuries pass on Earth. They could potentially travel across the galaxy within their lifetimes, but they'd return to an Earth where everyone they knew was long dead. This creates a fundamental asymmetry in interstellar travel. There's no going home in any meaningful sense. You'd be a time traveler to the future, unable to return to your own era. Are there loopholes? Science fiction often invokes wormholes, hypothetical tunnels through space-time that could connect distant regions. General relativity allows wormholes mathematically, but keeping them open would require exotic matter with negative energy density, which may not exist. Most physicists are skeptical that traversable wormholes are possible. Another speculative idea is the Alcubierre warp drive, which would contract space in front of a spacecraft and expand it behind, allowing faster than light travel without actually moving through space faster than light. But this too requires exotic matter and faces severe theoretical challenges. For now, the speed of light remains an absolute barrier, a cosmic speed limit that shapes not just how we travel, but how we think about causality, information, and the structure of reality itself. Einstein's insights transformed our understanding of the universe, revealing that space and time aren't fixed containers but dynamic participants in cosmic events. Having traced the universe from its explosive birth to its present state, we now face the most profound question of all. How will it end? The fate of the cosmos depends on the battle between expansion and gravity, and recent discoveries suggest the story might be stranger than we ever imagined. Heat death, the long fade to darkness current. Observations point toward what physicists call heat death, not a fiery destruction, but a cold, dark fading into maximum entropy. This is the consequence of the universe's accelerating expansion driven by dark energy. Here's how it unfolds. As expansion continues, galaxies beyond our local group accelerate away, eventually crossing our cosmic horizon, disappearing from view forever. In about 4 billion years, our Milky Way will collide and merge with Andromeda, forming a giant elliptical galaxy. Eventually, all galaxies in our local cluster will merge into one isolated island of stars in an increasingly empty cosmos. Star formation will continue for trillions of years, but the supply of gas will eventually run out. One by one, stars will burn through their fuel and die. The smallest, longest-lived red dwarfs might shine for 10 trillion years, but even they will eventually fade. By 100 trillion years from now, the last stars will flicker out. leaving a universe of dead stellar remnants, white dwarfs, neutron stars, and black holes drifting through the darkness. But the story doesn't end there. Given enough time, truly vast, almost unimaginable timescales, even these remnants will decay. Protons, the building blocks of atoms, may be unstable over timescales of 10 years or longer. If they decay, all atomic matter will eventually disintegrate into radiation. Even black holes aren't eternal. Through Hawking radiation, they slowly evaporate, with larger ones taking longer. A solar mass black hole would evaporate in about 10 years, while supermassive black holes could persist for 10 years. In the ultimate end, perhaps 10 years from now, in what's called the black hole era, the last supermassive black holes will evaporate in brief flashes of radiation. After that, the universe enters the dark era, a vast, cold, diffuse sea of photons and fundamental particles spreading ever farther apart, approaching absolute zero, maximum entropy, perfect uniformity. The heat death of the universe. It's a melancholy fate, but there's something profound in it too. The universe will have run its full course, explored every possible configuration, exhausted every source of free energy. It's not destruction, it's completion. The Big Crunch, a universe that collapse. Sheet death assumes the universe expands forever. But there's another possibility. If dark energy were to somehow weaken or reverse, gravity could eventually win, halting expansion and pulling everything back together in a big crunch. In this scenario, the universe's expansion would slow, stop, and reverse. Galaxies would begin moving toward each other rather than apart. Over billions of years, they'd collide and merge. The cosmic web would contract and temperatures would rise as matter compressed. Eventually, the universe would collapse back to a hot, dense state similar to the early moments after the Big Bang. The cosmic microwave background, now cold at just 2.7 degrees above absolute zero, would heat up, bathing the universe in increasingly intense radiation. Matter would disintegrate, atoms would break apart, and everything would compress into a final singularity, the opposite of the Big Bang. A cosmic implosion, however, current observations strongly suggest this won't happen. The universe isn't just expanding, it's accelerating. For a big crunch to occur, dark energy would need to reverse its behavior, and we have no evidence this will happen. Still, our understanding of dark energy is so limited that we can't completely rule out surprises. Cyclic models, eternal return. What if the end is also a beginning? Some cosmologists have proposed cyclic universe models where the Big Bang and Big Crunch repeat eternally, each cycle giving birth to the next in an endless cosmic rhythm. In some versions, the universe bounces at the moment of maximum compression, avoiding a true singularity. The collapse triggers a new expansion, a new Big Bang, and the cycle repeats. Each universe might have different physical laws and constants, a new roll of the cosmic dice. Other models invoke higher dimensional physics, suggesting our universe is a freeze-dimensional brain floating in a higher dimensional space. Collisions between brains could trigger Big Bang events, creating a multiverse of parallel universes being created and destroyed in an eternal cosmic dance. The ekpyrotic scenario, derived from string theory, proposes that the Big Bang was the result of two brains colliding. The universe expands and eventually the brains separate, only to collide again, creating a cyclic pattern. These models are fascinating but highly speculative. They require physics beyond our current understanding and are difficult to test. Most rely on aspects of quantum gravity, the marriage of quantum mechanics and general relativity, which remains one of physics' great unsolved problems. The far future. The black hole era. Between now and heat death lies an almost incomprehensibly long period, dominated by black holes. This is the black hole era, spanning from perhaps 10 years to 10 years after the Big Bang. During this era, black holes will be the most significant structures in the universe. They'll slowly merge, forming ever larger black holes. But even as they grow through mergers, they'll simultaneously shrink through Hawking radiation, a quantum effect, where black holes emit particles and slowly lose mass. The universe during this era would be unimaginably sparse and dark, black holes separated by distances far greater than the current visible universe. slowly radiating away their mass over time scales that make the current age of the universe seem like a blink of an eye. When the last supermassive black hole finally evaporates in a final burst of radiation, it will mark the end of any large-scale structure in the cosmos. Nothing but dispersed particles and radiation will remain. The ultimate fate of matter. What happens to matter in the very long term? If protons are unstable, as some theories predict, all atomic matter will eventually decay. Complex structures, planets, rocks, even the dead remnants of stars will disintegrate into showers of radiation and lighter particles. In some speculative scenarios, even the vacuum of space itself might be unstable. Our universe could exist in a false vacuum state, not the lowest energy configuration possible. If a region of space spontaneously transitions to the true vacuum, it would create an expanding bubble that converts everything in its path, potentially destroying the universe at the speed of light with no warning whatsoever. We'd never see it coming. But this is highly speculative, bordering on science fiction. What we know with reasonable confidence is that the universe will expand, cool, and fade. Stars will die, galaxies will darken, and eventually, even black holes will evaporate. The cosmos will approach a state of maximum entropy, not violently destroyed, but gently fading into a cold, dark equilibrium. It's a future measured not in billions, but in trillions and quintillions of years, time scales so vast, they're almost meaningless. Yet the fact that we can contemplate this fate, that we can peer billions of years into the past and project trillions into the future, is itself remarkable, a testament to human curiosity and the power of scientific reasoning. For all we've learned about the universe, the most profound truth is how much remains unknown. Some of the deepest questions in science concern the fundamental nature of reality. Itself questions where our best theories break down or point toward gaps in our understanding. The quest for quantum gravity, perhaps the most significant unresolved problem in physics, is quantum gravity, the attempt to reconcile quantum mechanics with general relativity. These two theories are spectacularly successful in their respective domains, but fundamentally incompatible in their descriptions of reality. Quantum mechanics governs the microscopic world of atoms and particles, where uncertainty rules and things exist in superpositions until measured. General relativity describes gravity and the large-scale structure of space-time, where everything is smooth, continuous, and deterministic. Both theories have been tested to extraordinary precision and have never been proven wrong in their domains. But they can't both be completely correct. Near black hole singularities, in the first moments after the Big Bang, and at the tiniest scales of reality, the Planck length, about 10 meters, both theories should apply simultaneously. Yet when you try to combine them mathematically, you get nonsensical infinities and contradictions. String theory is the most developed attempt at quantum gravity. It proposes that fundamental particles are point-like but tiny vibrating strings, and that space-time has additional hidden dimensions beyond the three of space and one of time we experience. Different vibration modes of these strings correspond to different particles. It's elegant mathematically, but it's proven extremely difficult to test experimentally, and there are a vast number of possible string theory solutions, a landscape of perhaps 10 different possible universes. Loop quantum gravity takes a different approach, suggesting space-time itself is quantized, made of discrete loops at the smallest scales, like a fabric woven from individual threads. This would mean space-time isn't smooth and continuous, but has a grainy structure at the Planck scale. Then there's causal set theory, which proposes that space-time emerges from a discrete set of events, connected by cause-and-effect relationships. And emergent gravity theories suggest gravity isn't fundamental at all, but emerges from deeper quantum phenomena like temperature emerges from the motion of atoms. Which approach is correct? We don't know. What's needed is a way to test these theories, observations, or experiments that could distinguish between them. This is extraordinarily difficult because quantum gravitational effects are only significant at energy scales or small distances far beyond our current experimental capabilities. The black hole information paradox. When Stephen Hawking discovered that black holes emit radiation and eventually evaporate, he created a profound puzzle. What happens to the information about everything that fell into the black hole? In quantum mechanics, information is never truly destroyed. It can be scrambled and spread out. But in principle, if you knew the exact quantum state of all particles now, you could work backward and determine what happened in the past. This is called unitarity, and it's a cornerstone of quantum theory. But Hawking's calculations suggested that black holes violate this principle. The Hawking radiation appears to be completely random, carrying no information about what fell in. When the black hole evaporates completely, the information seems to vanish from the universe, destroyed, not just hidden. This created what's known as the information paradox. Does information actually disappear, violating quantum mechanics? Or is it somehow encoded in the Hawking radiation in ways we don't understand? Or does it escape through some other means, perhaps into another universe connected via wormhole? Recent theoretical work suggests the information might be preserved in subtle correlations in the Hawking radiation or encoded holographically on the event horizon itself. The holographic principle, derived from string theory, proposes that all the information in a volume of space can be thought of as encoded on its boundary surface like a hologram. In this view, black holes are the ultimate holographic objects. With all their information stored on the event horizon, the paradox remains unresolved. But most physicists now believe information is somehow preserved. We just don't fully understand how. The solution will likely require a complete theory of quantum gravity and could reveal profound truths about the nature of information and reality, fine-tuning, and the anthropic principium. Of the most puzzling aspects of our universe is how finely tuned it appears for the existence of complex structures in life. Change certain fundamental constants by tiny amounts, and the universe would be sterile. No stars, no planets, no chemistry complex enough for life. For example, if the strong nuclear force were just 2% stronger, protons would bond so readily that hydrogen would be rare and stars couldn't form. If it were 2% weaker, atomic nuclei larger than hydrogen couldn't exist, and chemistry would be impossible. The cosmological constant dark energy appears fine-tuned to about 120 decimal places. If it were much larger, the universe would have expanded so fast that galaxies couldn't form. Why does the universe have these seemingly special values? One possibility is that we're asking the wrong question. The anthropic principle suggests that we observe these values because if they were different, we wouldn't be here to observe anything. It's a selection effect. We necessarily find ourselves in a universe compatible with our existence. This becomes more compelling if you accept the multiverse hypothesis. If there are countless universes with different physical constants, then it's not surprising we find ourselves in one of the rare universes where life is possible. We couldn't exist in the others, so of course we observe a life-friendly universe. But many physicists find this unsatisfying. It seems to abandon the search for deeper explanations, the why behind the constants. Perhaps there's a more fundamental theory that predicts these values uniquely, with no fine-tuning required. We simply haven't discovered it yet. Cosmic anomalies and unexplained observations. Putting aside the big theoretical questions, there are numerous observational puzzles that don't fit neatly into our understanding. The Hubble tension is one of the most pressing. Different methods of measuring the universe's expansion rate give slightly different values, about 67 versus 73 kilometers per second per megaparsec. The discrepancy is small but persistent and statistically significant. Does it indicate a problem with our measurements, or is it revealing new physics? Then there's the lithium problem. The Big Bang nuclear synthesis theory successfully predicts the abundances of hydrogen, helium, and deuterium, but it overestimates lithium-7 by a factor of 3. Where did the lithium go? Is our stellar evolution understanding wrong? Or is there something we don't understand about the early universe? The cold spot in the cosmic microwave background is an unusually large cold region. That's difficult to explain with standard inflation models. Could it be a statistical fluke, a signature of another universe colliding with ours? Or evidence that our universe has an unusual topology? Mysterious phenomenon like the WOW signal a strong radio signal detected in 1977 that has never been explained or repeated remind us that we might be missing important physics or astronomical phenomena. Most anomalies probably have prosaic explanations, but they're important because occasionally, anomalies reveal entirely new aspects of reality. Questions still awaiting answers behind these specific puzzles lie broader questions that define the frontier of physics and cosmology. What is consciousness, and how does it emerge from physical processes? Does quantum mechanics play a role, or is it purely classical biology? Is mathematics discovered or invented? Why is the universe so precisely describable by mathematical laws? Are we alone? Despite decades of searching, we've found no evidence of extraterrestrial intelligence. Is life rare, or does intelligence inevitably self-destruct? What came before the Big Bang? Does the question even make sense, or does time itself begin with the Big Bang? Why is there something rather than nothing? This might be the deepest question of all. Why does the universe exist? These questions don't have answers yet. They might not have answers for decades or centuries. Some might be genuinely unanswerable, limited by the nature of reality or our place within it. But that doesn't diminish their importance. Science progresses not just by answering questions, but by asking better ones. Each mystery solved reveals deeper mysteries beneath. The universe is like an infinite onion. Every layer we peel back reveals another layer below, each more subtle and profound than the last dot, and that's what makes the journey so thrilling. We're not near the end of discovery, we're still at the beginning, with vast territories of reality yet to explore. The mysteries remind us of how much adventure lies ahead. Recap of the cosmic journeyway. We traveled an incredible distance together from the first explosive moment of the Big Bang. Through 13.8 billion years of cosmic evolution, we've witnessed the birth of the first atoms, the formation of galaxies and stars, the synthesis of elements in stellar furnaces, and the emergence of planets where chemistry became biology and eventually consciousness. We've explored the invisible scaffolding of dark matter holding galaxies together, the mysterious dark energy accelerating the universe's expansion, and the extreme phenomena that push physics to its absolute limits: black holes, neutron stars, gamma-ray bursts, and magnetars. We've confronted Einstein's revolutionary insights about the nature of space and time, discovering that reality is far stranger than everyday intuition suggests, and we've peered into the far future, contemplating the ultimate fate of everything that exists. Most importantly, we've acknowledged what we don't know, the profound mysteries that continue to challenge our understanding and drive scientific exploration forward. But here's the most exciting part. This story isn't finished. We're living in a golden age of cosmology and astrophysics, with new discoveries announced regularly. The James Webb Space Telescope is revealing the earliest galaxies with unprecedented clarity, challenging our models of cosmic evolution. Gravitational wave detectors are opening an entirely new window on the universe, letting us observe colliding black holes and neutron stars. Next-generation particle accelerators may finally reveal the nature of dark matter or uncover new fundamental particles. Within the next decade, we might detect biosignatures in the atmosphere of an exoplanet, the first evidence of life beyond Earth. We could discover dark matter particles in deep underground laboratories. We might finally achieve nuclear fusion, unlocking the same energy source that powers the stars. The Square Kilometre Array, when completed, will be the most sensitive radio telescope ever built. Potentially detecting faint signals from the cosmic dark age is the era before the first stars formed. The Verisi-Rubin Observatory will survey the entire visible sky every few nights, creating a time-lapse movie of the cosmos and catching transient phenomena we've never observed before. These aren't distant dreams. They're active projects with funding, timelines, and teams of scientists working right now to make them reality. Contemplating the cosmic story changes our perspective on humanity's place in reality. We're not separate from the universe, we're part of it. A way the universe has become conscious of itself. Every atom in your body was forged in the heart of a dying star. The calcium in your bones, the iron in your blood, the carbon in your DNA, all were created in stellar furnaces billions of years ago and scattered across space by supernovae. eventually coming together on a small rocky planet to form you. You are, quite literally, made of stardust. Not metaphorically literally. The universe spent 13.8 billion years creating the conditions for your existence, assembling the elements, forming solar systems, evolving life through countless generations, all leading to this moment where you can look back and understand the process that created you. This cosmic perspective is humbling and empowering in equal measure. Humbling because we're insignificant on cosmic scales, a tiny species on a small planet, orbiting an ordinary star in a galaxy that's one of hundreds of billions. Our entire existence is a brief flash in cosmic time, yet empowering because despite our smallness, we can understand so much. A piece of the universe can figure out where it came from, how it works, and where it's going. Consciousness, the ability to wonder, question, and seek understanding might be the universe's greatest achievement, and we possess it. Never lose that sense of wonder. The universe is under no obligation to make sense to you, yet it does. Through observation, experimentation, mathematics, and reason, we've decoded cosmic mysteries that seem forever beyond human reach. You don't need to be a professional scientist to participate in this journey of discovery. Amateur astronomers regularly contribute to science, discovering asteroids, monitoring variable stars, and even finding exoplanets. Citizen science projects allow anyone to help classify galaxies, search for gravitational lensing events, or analyze data from particle physics experiments. But more fundamentally, curiosity itself is valuable. Ask questions, read about science, watch documentaries, visit planetariums and science museums. Look up at the night sky and remind yourself that you're seeing ancient light from stars, thousands of light years away, traveling through space and time to reach your eyes. Share your sense of wonder with others, especially children. Every scientist began as a curious kid asking why and how. Foster that curiosity, encourage questions, and never dismiss wonder as childish. It's the most sophisticated response to reality, recognizing that existence itself is astonishing. If this cosmic journey has inspired you, take the next step. Don't let this inspiration fade, turn it into action. Hit that subscribe button and enable notifications so you don't miss future explorations. We're going to dive deeper into specific topics: black hole physics, the search for life, the quantum nature of reality, and more. The comments section is where this community comes alive. Share your thoughts, ask questions, connect with others who share your sense of wonder. What fascinated you most? What questions are you still pondering? Your perspective matters. Science thrives on diverse viewpoints and challenges to assumptions. If you value this kind of content, consider supporting the channel through Patreon, channel memberships, or simply by sharing these videos. Creating high-quality educational content takes time and resources, and your support makes it possible. Use this as a starting point for deeper exploration. Check out the sources linked in the description. Read popular science books. Take online courses, follow space missions and scientific discoveries. The more you learn, the richer your understanding becomes, and the more questions you'll have, which is exactly how it should be. Go outside on a clear night and just look at the stars. Think about what you're really seeing: not tiny lights, but massive nuclear furnaces, scattered across unimaginable distances, each with its own story, many hosting planets, some potentially harboring life. That perspective shift from abstraction to visceral experience is powerful. We stand at a unique moment in human history. For the first time, we can trace our origins back to the Big Bang, understand the forces shaping cosmic evolution, and contemplate our ultimate fate. For the first time, we're searching systematically for life beyond Earth and beginning to understand what would make a planet habitable, the questions that kept our ancestors awake. Staring at the stars and wondering, we're actually answering them. Not all of them, not yet, but more than any previous generation could have imagined. And the questions we're asking now are even more profound than the ones we've answered. We're probing the nature of reality itself, the origin of everything, the structure of space and time, the possibility of other universes, the ultimate fate of existence. This is the grandest adventure there is, not exploring some distant land, but exploring reality itself. And you're part of it. By watching this, by thinking about these ideas, by sharing your curiosity with others, you're participating in humanity's greatest journey. The universe took 13.8 billion years to create beings capable of understanding it. Don't waste the cosmic gift. Stay curious. Keep questioning. Never stop wondering. Thank you for joining me on this journey through the cosmos. Until next time, keep looking up and keep asking why.